Problem number 2 reads, two flutes try to play the same note. The flutes are identical except that one is at a temperature of 0 degrees centigrade and the other is at a higher and unknown temperature T. The flute at 0 degrees centigrade plays a note of frequency 435 Hz. When played together, a beat frequency of 5 Hz is heard. What is the temperature T? Let's take a look at those two flutes. When the flute at 0 degrees centigrade plays the note, it's of frequency 435 Hz and sounds like this. When the flute at the higher temperature tries to sound the same note, it sounds like this. And when both flutes are sounded together, it sounds like this. We hear there a beat frequency of 5 Hz. From this information, you want to try to determine the temperature in this second flute. One hint before you try to solve this problem. You can find the temperature in this flute if you first find the velocity of sound in the air in this flute. Turn off your VCR now and attempt to solve that problem. The flute at 0 degrees centigrade plays a note of frequency 435 Hz. The flute at the unknown temperature plays a note of frequency that we'll call F. The beat frequency, this rise and fall in the intensity of the sound, occurs at the rate of 5 Hz. The beat frequency is equal to the difference between the two frequencies and would be equal to the unknown frequency F minus 435 Hz. And if we solve for the unknown frequency F, we get that that occurs at 440 Hz. The first thing I want to do is to find the velocity of sound in the flute at temperature T. I want to use, first of all, a basic relationship for waves, that the velocity of a wave is equal to its frequency multiplied by its wavelength. If I apply this to the flute at 0 degrees centigrade, I would have that the velocity at 0 degrees centigrade is 331 meters per second. This would be equal to the frequency 435 Hertz, or 435 per second, multiplied by the wavelength. Solving this for the wavelength, we get that the wavelength is 331 meters per second divided by 435 per second. And if you carry this out, you get a wavelength of 0.761 meters. Now that's the wavelength of the sound in the flute, in the air in the flute at 0 degrees centigrade. That would also be the wavelength of the sound in the flute at temperature T. That wavelength depends upon the length of the flute. So I want to use the same equation to find the velocity of sound in the flute and write that the velocity at temperature T then is equal to the frequency 440 per second multiplied by the wavelength 0.761 meters, and I get for this a velocity of 335 meters per second. Now we remember that the velocity at a temperature T is equal to 331 meters per second plus 0.6 meters per second per degree centigrade multiplied by the temperature T. And if I apply that now here, I would write 335 meters per second is then equal to 331 meters per second plus 0.6 meters per second per degree centigrade times the temperature T. The only unknown in that equation is the temperature T. If I solve for it, I would have T is equal to 335 meters per second minus 331 meters per second divided by 0.6 meters per second per degree centigrade. This is simply 4 meters per second divided by 0.6 meters per second per degree centigrade, and if you carry out that division, you come out with 6.67 degrees centigrade as the temperature in that flute. Alright, so 6.67 degrees is the unknown temperature of the second flute, and that solves our problem.